Hi everyone, in this video we're going to start topic 11 on nuclear chemistry, which is actually one of my favorite topics to talk about. It makes me a little sad we had to wait until the end of the semester to get to it, but I hope that you also enjoy this diversion into an interesting and new topic in chemistry. So this kind of ties in a little bit to when we had talked about radiation, and I think it was topic 6, I believe. We had talked about electromagnetic radiation, how we have microwaves and radio waves, and how we have UV waves, that sort of stuff. Now, those types of radiation are non-ionizing radiation. So this is non-ionizing, X-rays are ionizing, this is ionizing. But nuclear radiation, we typically get from only a couple of sources, and it is definitely ionizing radiation. And it has a lot of energy. It's got a really short wavelength and a high frequency. So some sources of nuclear radiation that we get on a regular basis are from the sun. We get UV light from the sun. It also outputs a lot of other types of higher radiation, which are stopped by our atmosphere and broken down by our atmosphere, so it doesn't reach us down on Earth. And then the other source of nuclear radiation that might come to mind first is things like nuclear power, nuclear weapons, let's see, I was thinking submarines for some reason, but we have a lot of other nuclear applications for this type of radiation. We also have natural radiation that comes from the environment around us. So if you look at where radiation is coming from, most of it is actually coming from background, from sunlight. We actually have some radiation that comes from the soil. If you've ever heard of radon gas, this is something that can come up from the soil. It's not really harmful because it's in such small amounts. It's not really going to cause any problems. But we also use radiation a lot in medical applications like X-rays. X-rays are X-rays, sorry. We use, if you think about nuclear radiation, we use it more in like PET scans, which we're going to talk about later in this topic. There's some in consumer products, which we're also going to talk about later in this topic. And then nuclear power plants account for a very, very, very small source of our overall radiation that we use. So let's take a look at nuclear radiation in perspective of all of our other types of radiation. So we had talked about radio waves that you hear whenever you turn on your car, that sort of thing, whenever you're listening to the radio, microwaves from, say, like a microwave oven. Infrared, this is going to be what we talked about with vibration of molecules. So we had mentioned how greenhouse gases are trapped in molecules, right? This is specifically to IR radiation. So IR radiation has to do with greenhouse gases and how they trap heat. Visible radiation is what you actually see. So these are the colors of the rainbow that we see with our eyes. So we actually see a very, very small portion of radiation. UV light comes from the sun. That's normally what we contribute to, say, tanning, that sort of thing. X-rays, so if you go in for a medical test and they need to X-ray your bones, they might use X-rays. And then we get up here higher into gamma rays. So somewhere in between our X-rays and our gamma rays is our nuclear radiation. So this type of radiation has a high energy. As you can see, it's got a high frequency too. It repeats a lot per second or per distance. It has a very short wavelength, which contributes to its relation to having high energy and a high frequency. Okay, so you might be familiar with nuclear chemical reactions you might have heard a lot about the nuclear power plant disaster that happened in Japan on 2011, that they're still dealing with the aftermath of this. I think recently, like maybe like last month or the month before, they were actually releasing nuclear waste into the ocean from this disaster in 2011. So this is still a relevant thing that's going on. and we're still feeling the effects of it. So we are exposed to nuclear chemistry all the time in our daily lives and in the news. Okay, so now we're going to play a quick game. So I'm going to ask you to see if you can guess the top countries here that have the most number of nuclear reactors. So these are countries that use nuclear power. See if you can guess like any of these here. Maybe you can get the top one or some of these other ones based on maybe what you've heard from the news or your knowledge of nuclear reactors. Okay, so in 2018, these are the number of nuclear reactors that we had in our top countries that use nuclear power. The United States is actually number one for the amount of the functioning nuclear reactors that we have, or operational nuclear reactors. France comes second with 58 nuclear reactors, China at 46, and then Japan just below it. So these are our top countries that use nuclear power to power homes and all sorts of applications. So let's explore why nuclear chemical reactions are so unique and interesting and how they create power that we can harness and use for all kinds of applications. So what's unique about nuclear chemical reactions as opposed to our, say, like double displacement reaction or precipitation reactions that we learned about is nuclear chemical reactions can disturb all parts of the atom. When we had discussed double displacement reactions, we had only discussed valence electrons. We had only said that these were the electrons that were moving. So if you have, say, Na, and it combines chemically with Cl, these things stick together, one of the valence electrons from sodium moves to chlorine, because chlorine has 7, to create Na+. It's missing a valence electron, and Cl-. Now it has 8 electrons. If you'll notice here, what moved was a valence electron. Nuclear chemical reactions don't act this way. They can pull electrons from here, from interior electrons. They can pull protons from the nucleus. They can pull neutrons from the nucleus. So they kind of get in there and shake everything around in the atoms, which causes a very unique reaction. So nuclear chemical reactions can disturb all parts of the atom, electrons, protons, and neutrons, as opposed to normal chemical reactions where we're only seeing valence electrons react. Let's take a look at nuclear decay. This is a natural process that happens. There is, like I said, radiation in the soil, radiation and all kinds of stuff around us, and over time these chemicals break down, and it just happens naturally. Chemicals always like to be in a more stable form, and so nuclear chemicals do this. So an example is radon. This is a chemical that undergoes what's called alpha decay because its nucleus is unstable. Something you'll notice about radon that's pictured here, this is the nucleus. It's got a lot of protons. It's got a lot of neutrons. This is a very big atom compared to what we're used to working with. Normally we work with stuff that's at the top of the periodic table, but with nuclear decay we work with stuff that's at the bottom of the periodic table. Because these atoms are really big, it makes them unstable. So a lot of these are radioactive at the bottom of the periodic table. So radon here, this is its mass. This is the number of protons that it has. When it undergoes alpha decay, it's a spontaneous process. So it does this until it becomes a stable atom, and it emits radiation to do this. So here's how this works. So radon decomposes into this Rn atom, which I can't remember for the life of me what the name of it is on the periodic table, but you'll notice that the mass of this new atom is different. It's lost 4 mass values, and protons, it's lost 2 protons. Whoa, that's really weird, right? Okay, and so those go over here into this new chemical that's created, this helium, which is this helium, He2 plus, I think, He2 plus. So it's got 2 protons, 2 neutrons, no electrons, and this is what we call alpha radiation. It's a helium nucleus. So essentially what we're seeing is radon splits into 2 different atoms. This is not something you've ever seen before. This is why I kind of think of nuclear chemistry as, like, say, alchemy, right? So you're taking one element and you turn it into a completely new element. You split it into 2 separate new elements. It's really like creating something from nothing, and I think that's super duper cool. So let's take a look at this alpha particle that I had talked to you about. So you might be thinking that helium's a noble gas. That's not radiation, right? Okay. This is radiation. Let's look at the difference here between, say, a helium atom and a helium alpha particle or a helium nucleus. So the difference here is that helium gas from the periodic table, if we look at it, it's got 2 protons, all right? The helium alpha particle that's down here, it's got 2 protons too. Neutrons, helium gas, it's got 2 because it's got a mass of 4, so 4 minus 2 is 2. Helium alpha particle also has 2 because 4 minus 2 is 2. We have a chemical formula for helium gas, which is He, but for helium alpha particle, it's helium 2 plus. Okay. So based on this, how many electrons would your helium gas have, and how many electrons would your helium alpha particle have? What you're going to find here is, if you look at the periodic table, we see that the electrons from our helium gas, we're going to have 2 of those here from the periodic table. But if we look at our helium alpha particle, it has 0 electrons because it's got a 2 plus charge. So it's lost all of its electrons. And that's what makes it radioactive. This causes that radioactivity. Because it's really unstable, which means it reacts with all kinds of things around it really quickly. And so this is what we call a helium alpha particle, or you might hear it called a helium nucleus. So make sure to write those terms down so that when you hear them, you don't get them confused. They are the exact same thing. So let's review isotopes. We had discussed in previous topics what an isotope is. I think this was like topic 1. So we should take a look at this again because isotopes are heavily involved in nuclear chemistry, so I need to make sure that you understand this concept first. So one of our famous isotopes that you might have heard about before is uranium. So uranium-238 is our natural uranium that occurs in the soil. Uranium-235 is what you might have heard of as enriched uranium. It's the one that's radioactive. And this one is very mildly radioactive. Whereas this one is very enriched, is very radioactive. Okay. So uranium-238, the difference here between 238 and 235 is their mass. So what we're seeing here is they have the same number of protons, but they have different numbers of neutrons. So here we have 146 neutrons, here we have 143 neutrons. And by changing this amount, we get a different atom that reacts differently. So let's dive into our isotope notation just to remind ourselves about how we note these things, because you're going to be seeing this a lot in our nuclear chemistry. So on the periodic table, we've got our atomic number up here, which is our number of protons. Our isotope notation, we put that number down here. So this is number of protons. Then our mass number on our periodic table is usually below the element or the chemical symbol. And our isotope notation, we put it above. This is just a notation that we have used for centuries and ages, so you'll just have to get used to seeing it because we can't fix it, even though it doesn't really make any sense. So don't get those mixed up. They are flipped if you see isotope notation like this. Okay, so let's try to do that with our uranium-235 and 238. So how would you write U-235 from this notation here and write it in our isotope notation? Like the example that I showed you right here. So how we would do this is we need the number of protons and we need the mass number. The mass number is here, so that's easy. Our uranium, the chemical symbol is a U. The number of protons for this one is 92, and the mass would be 238, or for U-235, you'd have U, 92, and 235. So that's how you would write both of these. Now, sometimes in nuclear reactions, we see that single neutrons, protons, or electrons are emitted from the reaction. So this is an alpha particle. This is our biggest type of nuclear radiation. So this is our alpha particle. If it had a 2+ here. But sometimes just a single neutron leaves, or just a single proton leaves. You might have, say, our radon, or here, let's look at uranium, because I remember that one. 238, 92. Sometimes just a neutron comes off. And the new chemical that we would make would be U-237, 92. So we need to indicate that this neutron is lost. And it's not necessarily a chemical from the periodic table. So we write these in isotope notation. So if a neutron's chemical symbol is N, so just like how helium is He, if it's N, how would we use isotope notation to denote a lone proton or a lone neutron by itself that gets emitted from a nuclear reaction? What you'd want to do here is you need the mass of the neutron and you need actually the charge of the neutron. So the mass of the neutron we know is 1. So our mass goes up here. Now, our atomic number, there is no atomic number. It's not on the periodic table. That doesn't make sense. So we actually put our charge down here. So the N1, 0. This is how we would use isotope notation to denote a neutron. Okay, now try this with a proton. How would you denote a proton if the chemical symbol for a proton is P? What you want to do here is the same thing. You need the mass, like we had in the previous one, so it would be 1. The charge on a proton is +1. So it would be a 1 and a 1. Give this a shot for an electron now. If the chemical symbol for an electron, we assume, is E. So what you'll find is the mass on an electron is 0. They technically don't have enough mass to merit us taking them into account. The charge on an electron is -1. So you'd see it written like this if we looked at the isotope notation for a lone neutron, a lone proton, and a lone electron.